Okay, so in this video we're going to talk about system of equations in three variables. A linear equation in three variables is an equation that can be written in the form ax plus by plus cc equal to d, where a, b, c, and d are real numbers, and a, b, and c are not all zero. A solution of a linear equation in three variable is an order triple of numbers of the form x, y, z, whose coordinates satisfy the equation. For example, the order pair or the order triple 1, 2, -6 is a solution of x plus y plus z equal to -3, since substituting these values into the equation gives a true statement, right? So we get 1 plus 2 minus 6, well, that's equal to 3 minus 6, which is -3, which is a true statement. The graph of an equation of the form ax plus by plus c equals d can be drawn in three-dimensional coordinate system with three axes. The graph of such an equation is called a plane. Okay, so let's see what a plane looks like. So you could, and I'm going to go ahead and use Desmos to visualize this. So Desmos has a 3D app that's in beta stage right now. So you can think of a plane as like an infinite paper. So think a rectangular piece of sheet of paper that's very infinitesimally thin, spreading out in all directions. It's flat. Okay, so let's go ahead and let's examine the equation that we just verified the order pair 1, 2, -6 was a solution to. So x plus y minus 6 equals -3. I forgot the z part, or excuse me, sorry, it's x plus y plus z equal to -3. That's our order, that's our plane. And you can see it. It's an infinite thin sheet of paper, for instance. Okay, so when we verify the order pair, or excuse me, order triple, we have the order triple of 1, 2, -6. And what we'll see is the point, it just should lie on there, but unfortunately we don't see it because we don't have the right viewing. Okay, and so here's the point that you can see now. That point there will be a point on that plane. It would have coordinates of x equal to 1. So if we look this way, we would see that x has a 1, and then y coordinate would be 2, and it'll be the bottom of the z-axis to at -6. And so a plane consists of an infinitely many points that will satisfy the equation, and any point that's on the plane there will be a solution. Okay, let's go back to the notes. Okay, so a solution of a system of three linear equations. So now we have a system of three linear equations. So a solution of a system of three linear equations in three variables is an order triple that satisfies each equation of the system. So here we're asked to determine whether the order triple -4, 2, 5 is the solution of the system, and to do so we need to plug in the order triple into each one of these equations to see that we get a true statement. So I'm going to go ahead and substitute. Okay, so we're gonna have to compute here, and we see that we get a -8 plus 6 plus 20. -8 plus 6 here gives us a -2, plus 20 gives us 18. So we could see that 18 does give us 18, and that's a true statement. All right, so the first equation checks. What about the second equation? We get 3 times -4 plus 4 times 2 plus 5 equal to 1. And once again, simplifying here, that's the question right here. Does that add up to 1? So we get -12 plus 8 plus 5. We have a -12 plus 8, which is -4, plus 5, which gives us 1. And so we can see that 1 does indeed equal 1, and the second equation also checks out. Now the third equation here, x plus y plus z, 3z equals 13. Well, what do we have? We have -4 plus 2 plus 3 times 5. Does this add up to +13? So we have a negative 4 plus 2, which, well, we can't do the order of operations. So they do the multiplication first. So we'll write this step here to get 15. Negative 4 plus 2 gives us a negative 2, and then plus 15. So that gives us 13. And so indeed, 13 does equal 13, which satisfies the third equation. And since the ordered pair satisfies all three equations, we say negative 4, 2, 5 is a solution of the system. Okay, so just like in the system of equations of two variables, where we had when we had a solution, that means the lines met at a single point or intersect at a point. Well, likewise, the three planes that each one of these equations represent will intersect or meet at a single point. And we'll go ahead and use Desmos app here again, and to verify that. So I already inputted the equations. Let's go ahead and turn them on here into our equation. And you can see that they're crossing each other, meeting at various points. However, where they have a solution, it's going to be where they meet. And it's kind of hard to tell, but it appears they're going to meet somewhere about right there. And to verify that, we're going to go ahead and plot the point negative 4, 2, 5. And you can see it's kind of hard, but that's that point there. They all cross at that individual point, or they meet at that single point there. All three can simultaneously meet at that point. And so that's how visually it would look like. Okay, so just in the case of two variables, this is a three-linear equation. Three variables can have exactly one solution, no solution, or infinitely many solutions. Okay, so here is a summary or a quick summary of that. So when we have a consistent system, that means all the planes, like the example that we just got right now, had a solution, and therefore they met at a single point. So three planes intersect at a single point, the system has one solution. A consistent system is when all three planes have a line in common. The system has infinitely many solutions. And then, of course, there we have inconsistent systems. And here's three situations where they're inconsistent, right? They could meet at a single line like this, right? They all meet there, but that's inconsistent because there's not a single point where they all meet at. And then you could have parallel planes that don't even meet at all, and therefore they have no solutions. And then, of course, you could have something like that where two planes are parallel and the other ones meet. Okay, and so the three planes have no point in common to all three. The system has no solutions. Okay, so that's how pretty much summarizes the three cases again. So to solve a system of three linear equations in three variables, we can use the elimination approach. We write each equation in standard form, ax plus by plus cz equal to d, in clearing decimals or fractions. 2, pick any two equations and eliminate a variable. 3, pick a different pair of equations and eliminate that same variable as in step 1. 4, solve the resulting pair of two equations and two variables. 5, to find the value of the third variable, substitute the values of the two variables found in step 4 into any equation containing all three variables and solve the equation. And then 6, which I'm going to probably not do here just because the video will be pretty long if I continue that. If I tried that, we probably will skip step 6. So check and propose solution in all three of the original equations. Write the solution as an ordered pair. All right, so let's see. Here we have our first system. We have 3x plus y plus 4z equal to 12. X plus 2y plus 2z equals 9. 3x minus 3y minus 2z equals 1. Okay, so I'm going to give these some labels here. So this is equation 1, equation 2, and equation 3. And what I'm going to do here is, they're all in standard form already. We had no decimals or fractions, so we're good. So basically the first step's done. Now I'm going to pick two equations and eliminate a variable. And I'm going to go ahead and eliminate the z variable. And the one way to do that is say add equation 2 and 3. Okay, so if we add equation 2 and 3, so we have x plus 2y plus 2z equals 9. Equation 3 is 3x minus 3y minus 2z equals 1. If we add these together, I would get 4x minus y. And the z's would cancel there, equals 10. So I'm going to call that equation 4. Alright, so now I pick a second pair of equations that are different from the first pair and eliminate z again. So this time what I'm going to do is multiply equation 2 by negative 2, then add equation 1 to the result. Or I should say maybe the result to the equation. All right, so in other words, multiplying equation 2 by negative 2, I have negative 2x minus 4y minus 4z equals 18, negative 18. Okay, and then I'm going to add equation 1 to this result here. So equation 1 gives us, we have 2x plus y plus 4z equals 12. And so I'm going to add these up. So the x's cancel. Negative 4y plus y gives us negative 3y equals negative 6. And then clearly this is another equation 5. Technically this would have been a system of two equations, two variables, but I got lucky and my x got eliminated. Therefore, I already know what y is by solving for y here to get y equals positive 2. And now I use that value and I'm going to substitute back into equation 4 here and solve for x. Okay, so then that would give me 4x minus 2 equal to 10. So we have 4x equals 12, and dividing both sides by 4 there gives me x equal to 3. And so now I have two of the variables, x and y now. Now I use each of these two variables and substitute back into equation 1, 2, or 3. I'm going to just go ahead for simplicity, sub back into equation 1. Okay, so doing so, well, equation 1 was 2x plus y plus 4z equal to 12. So let's go ahead and plug that in. So 2 times 3 plus 2 plus 4z equals 12, right? So in other words, sub back into equation 1, and I probably should say solve for z. Okay, so doing so, what do we have? We have 6 plus 2 plus 4z equals 12. So we get 8 plus 4z equals 12, which tells me 4z equals 4, which we get z equals 1 dividing both sides. All right, so now that we have our x, our y, and z, you could check to see that it's a solution. I'm not going to do that, but that's how you would determine if it works or not. But the solution is the order triple 3, 2, 1. Okay, so let's try this next example here. Solve the system 4x minus 3y plus 5z equal to 23, 2x minus 5y minus 3z equal to 13, negative 4x minus 6y plus 7z equal to 7. I'm going to go ahead and label these as equation 1, 2, and 3. Okay, so this time I'm going to eliminate x. And the way I'm going to do that is first take equation 1 and 2 and add them. Sorry, 1 and 3 and add them. Alright, so equation 1 is 4x minus 3y plus 5z equal to 23. Equation 3 is negative 4x minus 6y plus 7z equal to 7. Alright, so we're going ahead and add them. We see that the x's cancel. We get negative 9y plus 12z equals 30. All right, I'm going to call that equation 5, or excuse me, equation 4. Okay, next I'm going to take a different pair of equations and eliminate x again. So this time I'm going to take equation 2 and equation 1. So what I'm going to do here though is multiply equation 2 by a negative 2, then add the result to equation 1. Okay, so let's multiply equation 2 by negative 2. So I get negative 4x plus 10y plus 6z equals negative 26. Okay, so that's equation 2 multiplied by negative 2. And then I want to add this result to equation 1. So here's equation 1, 4x minus 3y plus 5z equal to 23. All right, so you can see my x's cancel. I'm going to get 10y plus negative 3y to get 7y. And then I'm going to get 11z. And then negative 26 plus 23 gives us a negative 3. So I'm going to call that equation 5. Okay. All right, so now equation 4 and equation 5 is essentially an equation in two variables, a system of two equations and two variables. And so we can do elimination all again with these two equations. All right, so I'm going to do the following. I'm going to multiply equation 4 by 7 and multiply equation 5 by 9, and then add the results. All right, so let's see how that looks. So multiplying equation 4 by 7 would give us negative 63y plus 84z equals 210. Now taking equation 5 and multiplying by 9, we get positive 63y plus 99z equal to negative 27. Okay, those are the results of doing that. Now we're going to add those two equations to get, so negative 63y and 63y cancel, and we're going to get 183z equal to 183. Since 210 minus 27 is 103. Now dividing both sides by 183 gives us z equal to 1. Okay, so now we're going to use equal to 1. And come back up here again and substitute. Sub back into equation, say, 4. And solve for y. Okay, so then I'm going to take my negative 9y plus 12z, but plugging in my 1 for z equals 30. So we get negative 9y plus 12 equals 30. So negative 9y equals 18. Dividing both sides by negative 9 gives us y equal to negative 2. All right, now I know z, now I know y. Now we're going to sub back into equation, say, 1. You could substitute either into equation 1, 2, or 3. I'm just going to go ahead and take equation 1 here and solve for x. All right, so 4x minus, 3y plus 5z equals 23. Okay, so let's plug our values in. So we have 4x minus 3 times negative 2 plus 5 times 1 equals 23. All right, so we have 4x plus 6 plus 5 equals 23. So we get 4x plus 11 equals 23. And so subtract 11 on both sides there to get 23 12. Okay, and then divide both sides by 4 to get x equals 3. Okay, so we could see that the solution is the order pair 3, -2, 1. All right, let's take a look at the next example here. So we're asked to solve the system 2x plus y minus 3z equals -3, 3x minus 2y plus 4z equals 2, 4x plus 2y minus 6z equals -7. All right, I'm going to label this as equation 1, equation 2, equation 3. All right, the first equation here, we're going to multiply equation 1 by 2 and add the result to equation 2. So then we're going to add the result to equation 2. Okay, so multiplying equation 1 by 2 gives us 4x plus 2y minus 6z equal to -6. And we're going to add this result to equation 2, so that's 3x minus 2y plus 4z, and that's what we're trying to eliminate y here. And there you can see that canceling, we're left with 7x plus or minus 2z equals -4. All right, so now let's call that equation 4. All right, now I'm going to take a different pair of equations and eliminate y again. This time I'm going to work with equation 2 and 3. So I'm going to add equation 2 and 3. Okay, so we have 3x minus 2y plus 4z equals 2, 4x plus 2y minus 6z equals -7. Okay, the y's cancel again. We have 7x plus or minus 2z equal to a -5. Equation 5 here. And now we can see we have a new system here, 2 equations and 2 unknowns. One thing to note is the left-hand side are both identical, and they're both equaling 2 values that are not the same on the right-hand side. So this probably is going to mean we're going to get some kind of inconsistency here, because you can't have one side equal the same and the right-hand side equal to another value. Not possible. So to see this, let's go ahead and say multiply equation 4 by -1, then add result to equation 5, and basically to eliminate, say, x, for instance. All right, so if we did that, what do we have? -7x plus 2z equal to 4. Equation 5 is 7x minus 2z equal to -5. And so we can see the x is canceling, but we also see the z's canceling, giving us 0 equals -1. And that there is what we call a contradiction. In other words, there's no solution which means the system is inconsistent. Okay. When the equations in a system of 2 equations and 2 variables are dependent, the system has infinitely many solutions, which means the system is a consistent system. A system of 3 equations can have dependent equations and still be inconsistent. And so just kind of summarize that, when all planes coincide, the equations are dependent and there are infinitely many solutions. A system is consistent. Another possibility a system is consistent is when the 3 planes intersect in a common line. the equations are dependent and there are infinitely many solutions. But you also have a system which is inconsistent, and this can be when two planes coincide and are parallel to a third plane. The system is inconsistent and there are no solutions. So let's see an example of maybe where that might happen. So this next example here, we're actually solve the system. 4/5 x minus y plus z equal to 53 over 5. X minus 2y minus z equals 8. 0.2x minus 0.3y plus 0.1z equal to 2.3. Okay, so I'm going to go ahead and clear the fractions and clear the decimals. So the first equation here, I'm going to multiply it by 5 on both sides. And doing so would give me 4x minus 5y plus 5z equals to 53. All right, the second equation here I'm going to leave alone, but the third equation I'm going to go ahead, well, before I do that though, we have 53 here. Second equation I'll leave alone. I'm just going to call that x minus 2y minus z equal to 8. But the third equation here, I'm going to multiply both sides of this equation by 10 so that we could get the new equation, 2x minus 3y plus z equal to 23. And I'm going to call this equation 1, equation 2, and equation 3. Okay, so I'm going to go ahead and eliminate z by first multiplying, say, equation 2 by 5, and then I'm going to add the result to equation 1. All right, so multiplying the first equation 2 by 5, we're going to get 5x minus 10y minus 5z equals to 40. Okay, and then I'm going to add this result to equation 1, which is 4x minus 5y plus 5z equal to 53. So we're going to add those up, and we see we're going to get 9x minus 15y equals 93. So I'm going to call that equation 4. All right, then to get it, I'm going to eliminate z again by taking a different pair of equations. So I'm going to take equation 3 and 2 and add the results. So I'm going to add equations 2 and 3. So we have x minus 2y minus z equals 8. 2x minus 3y plus z equal to 23. And we're going to go ahead and add the results there. So we're going to add these two equations to get 3x minus 5y equals 31. So let's call this equation 5. So we eliminated z. Now we have a new system, equations 4 and 3. I'm going to go ahead and multiply. I'm going to eliminate, say, try to eliminate maybe x, for instance. So I'm going to go ahead and multiply equation 5 by, say, -3 and add the result to equation 4. Okay, so then now we have -9x plus 15y equals -93. So that's equation 5 multiplied by -3. And then I'm going to add this result to equation 4, which is 9x minus 15y equals 93. And when you add these two equations, the left-hand side gives us 0, right-hand side gives us 0. Okay, which means that we have the equations are going to be dependent. and the solution has infinite many solutions. Or then the system has infinite many solutions. All right, let's move on to the next problem here. Mary inherited $15,000 and invested part of it in a money market account, part in municipal bonds, and part in a mutual fund. After 1 year, she received a total of $730 in simple interest from 3 investments. The money market account paid 4% annually, the bonds paid 5% annually, and the mutual fund paid 6% annually. There was $2,000 more invested in the mutual fund than in bonds. Find the amount that Mary invested in each category. All right, so X here, we'll say is the amount invested in a money market account. And we'll say Y is the amount invested in bonds. Okay, and then Z is the amount invested in the mutual fund. All right, we're talking about simple interest here. So simple interest, the formula is the principal, how much you invested, times the rate at which you're getting, and times the how long. So clearly this is 1 year, so T equals 1, just leaves us basically with how much money we're investing times the rate. All right, well, before we use that formula, we know that X plus Y plus Z, right, the sum of how much we're putting into each category or each account here, has to add up to $15,000 because that's how much Mary inherited. Okay. The next equation here is where we're going to use the simple interest for each account. The first account, the money market account, is paying 4% interest. So we don't know how much we put in, but the percentage or the rate here, R, would be 0.04 times the amount we put in that account. So that's represented by X. Plus, the bond is paying at 5% interest, so it'll be 0.05 times the amount we put in the bond. And then Z, or excuse me, the amount we put in the mutual fund times the amount it's paying annually, which is 0.06 Z. We know that there is going to add up to $300. Sorry, not 300, $730. Okay. All right, and then the last information they gave us says there was $2,000 more invested in the mutual fund than in bonds. And so that means Z is equal to $2,000 plus Y. And that there is the system of 3 equations and 3 unknowns. I'm not going to show the solution to or show how to arrive at the answer, but you can fill in the details here and you should arrive at $7,000 that was put into the X account, $3,000 put into the bond account, and then $5,000 was put into the mutual fund. Okay, so once again, that's the money market account, the money market account. This was bonds, and this was the mutual fund. All right, that's it for this video.